All right, welcome to local modeling. So local modeling. Oh, I gotta do this first. This one. Local modeling. So we talked about really calculated through 3 different examples. I'm not actually going to do bilinear example here. I'm going to do it in another video, but I'm going to do nearest neighbor and I'm going to do IDW because those ones are really more common than the bilinear, because you need to have like a perfect square to do bilinear. Otherwise it doesn't really work very well. So this local modeling is to just get started very easily. So we're going to start with nearest neighbor. And with nearest neighbor, what we're looking for is the minimum distance to assign the Z value. So when I go through, I'm going to take my distance. So we're looking for distance between X and Y. So we take the change in X squared plus the change in Y squared, that's Y, to get our distance. Don't worry about Z because we don't know what Z is. So let's say we have our point, and our point is at 50-50. P is at 50-50. Okay. So we're going to use the same idea in the global modeling because we use the same numbers. So I'm looking for the minimum distance to 50, like in both X and Y. That's where I'm placing it because I don't know what the elevation is here. So I'm going to use just a Euclidean distance. And then I am going to calculate that through. And I have my values that show up here. So I'm just going to place that over top because you don't need to see those letters. So there are my distances. So I'm going to look through this. This is as hard as it gets. So I calculate the distance for every single one of these points. So I'm using X and Y for point 1 all the way to point 15 for point P. So I calculate it. I find this is 50 meters. I calculate it using these ones. I find it's 50 meters. Calculate the next one is about 20 meters, etc., etc. I'm not even looking at the Z at that moment. So then what I'm going to do, so that's the first step, is doing this. My second step is trying to determine the minimum distance. So you can sort, if you're using Excel, you can sort, you can do whatever, you can use your eyes. So if we go through and let's say we're using our eyes, we see, oh, there's an 8. So it looks like, and nothing else is really below 10. So it looks like this point here is going to be the minimum distance. So my minimum distance occurs at 0.7. It's not. And therefore my PZ value is going to be the same value as the Z, so it is 60.5 meters. Done. That's as easy as nearest neighbor gets. Our next one, so that's number 1, IDW, is also not too bad because it's really just a formula. So we're going to stick with the P at 50-50. We're trying to figure out what the height is at that location. So my IDW has the formula that our Z value is equal of whatever our point is equal to Z of the point. Sorry, Z I divide sum of the ZI divide by the distance. Sum. There we go. Sorry. Sum. Let me just totally rewrite that because that's just a disaster. Okay. Do the sum of brackets ZI divided by D weight I, and that's all divided by the sum of 1 over the DI weight. Writing at an angle here. So this is the formula that we use. So what I do, and I'm going to say, just to keep things simple, I'm going to say the closest 6. We're going to use the closest 6 for this. So I'm using so because I'm stating how many number of points, this is an irregular patchwise function, right? So I'm going to look for the closest 6. So where are my closest 6? So let's use purple for this one. Whoops. So looking at my nearest 6, so I know that this one is nearest, and then my next one would be probably 13, and then 16, 17, 20, with that is 5. If I have another 20, so 25 is this one. So everywhere that I have a purple marker, those are the points that I'm going to use to be able to calculate my my elevation at P. So what that looks like now is, so my ZP is equal to, on my numerator, which is, this is going to look huge even though I'm only using 6 points, I use the Z value, so I use 60.5, and I divide that by the D value. Now if I was to square, let's just use squaring. I'm going to square and square distance. So my weight is to 2, so I have a distance to 2. So my distance, do I want to square it? I don't know if I want to square it. Yes, I do want to square it. Okay. So my distance on the bottom is 8.75 squared. And then I add my next one. So I'm just going to go from the top down instead of the closest to the bottom. So my top one is at 46, getting dyslexic, 46.9 divided by its distance, 20.75 squared, plus 84, or no, that's the distance. I know that's right, it's the height, 84.6 divided by the distance, which is 17.67 squared, plus the next one. So I have 3.5 divided by 13.91 squared, plus 17 divided by 16.5 squared, plus 22.7 divided by 25.1 squared. Okay, that is my numerator. Now I'm going to do the denominator, which is really a repeat of everything that we just did, except I keep out the Z value. So 8.75 squared plus 1 over 20.75 squared plus 1 over 17.67 squared plus 1 over 13.91 squared plus 1 over 16.5 squared plus 1 over 25.1 squared. There we go. So once we calculate that through, we end up with a Z value of 44.35, whatever meters. Well, should only have one decimal to that. I keep putting extra decimals on. It's actually 3/4 something, so we'll leave it at that. There's my Z value for point P. How different is that from my nearest neighbor? Very different, right? So that is to keep in mind here, that your values are going to look very different. Which one's more accurate? That is up for you to decide, right? So again, there are statistics to go through this. I'm not getting into the statistics for this class, but especially on local modeling, because it basically takes the F statistic one step further. So we're going to leave it at that, but I want to show you how different these models really come up with, right? So if we go back to the p-value that we had with our global model, our first order was 69, so we have global. So we had the first order, which was 69.8. The second order was 72.5. Nearest neighbor is 60.5, and my IDW is 44.3. Which one of those is correct? Of course, we said that the global models weren't showing up very accurately, so we figure, okay, well, that's out. But the nearest neighbor is pretty close, so that probably would make more sense. But the IDW is really much lower. So is this an outlier, or is it actually accommodating for all the error that's put up in here? So how do you answer that question? It really depends on your application. It depends on your confidence. It depends on, you know, what your ground looks like, right? So obviously this ground is not very, I mean, we can see here that between 2 points, it goes from 3 to 80. so it's a pretty crazy data set. So what is more accurate in this case, we don't know. We'd have to go out and validate. If you were getting numbers this crazy like this, go out and validate it. Check it. Go out there and see which one. Get some actual data. That's going to be a lot better than doing this. But if you are, if you have a real data set that's not like crazy numbers like what I just made up here, you're going to see it's going to be a lot closer. And so I do suggest that you're going to see these much closer. So they're going to be within like 10 centimeters. So a lot of the times we use our models for creating roads or just, you know, oh, we need this extra point in here to create a design for something. That's when you would start applying some of these values. So that is, that's an example with a kind of a random data set with really small numbers. So any kind of little change within really small numbers makes a really big difference. So you're going to see larger numbers for data sets, of course, in the real world. Yeah, but I'm just keeping them small here and simple. And otherwise, that's local modeling. I'll do a quick example of bilinear in another video, and that'll just be a short one. So, but that is local modeling for you guys, and if you have any questions, please let me know in class.